Hello everyone, and welcome to this video where I'll be taking you through a sample question related to the objective determine the derivative of a parametrically defined curve with exponential and logarithmic functions. So I'm at Knewton.com right here in their Knewton Alta program. That's where this question is coming from. And, it's related to the objective mentioned in the title. And I'm in this instructor mode here, so you're seeing something a little different than what you'd be seeing as a student. But still, I just want to go through, how to work on a problem from this particular objective. And if you see one, all the others are pretty similar. Now, if you have familiarity with the topic already, I would suggest you pause the video, try to work it out on your own first, and then come back, watch me go through it, and compare your work to mine, see how well you're grasping things. All right, so here we're asked to determine the derivative of the parametrically defined curve represented by the equations x of t equals 4 times the natural log of 2t plus 2, and y of t equals 2 minus 4 times the natural log of 4t. All right, so these two equations, right? Remember how equations defined parametrically represent a curve on the, in this case, will be on the xy plane, where the x and y coordinate depend on this parameter called t. And, as you change the value of t, increase the value of t, you'd be tracing out some curve on the xy plane. So we're trying to find the slope of that curve at any moment. Now I know you can see the answer here already, but I'm going to show you how we got there. And I'm in this instructor mode. You can see the answers. But that's, dy over dx, right? Y prime of x, the derivative, the slope of the tangent line to the curve traced out by these equations on the xy plane. All right, so I'll go about how to do that real quickly. Now, one way to do it would be to, now I wouldn't recommend this. I'll show you a better way, but one way to do this would be to eliminate the parameter. So you solve one equation for t and substitute for t in the other equation, and then you get a rectangular equation, something with just x and y involved, no t, no parameter. Or find some relationship between x and y, here that would enable you to write the equation in just x and y only. And then from there, find your y prime, find dy over dx, either implicitly or explicitly. But a much quicker way is to leave the equations in parametric form, and you can find the derivative in terms of that parameter though. Okay. So now this one ends up being a constant, I see, but quite often you'll see the derivative be some expression involving the parameter. So if you want to find the slope of the tangent to a curve at certain points, you need to know the value of the parameter there in a lot of cases. That won't be the case here, but I've seen it in previous videos I've made, and we'll see it, I'm sure, in future videos. Okay, so there's some paper here. So the equations given, right, the parametric equations for the curve were, the x coordinate in terms of t was 4 times the natural log. Remember, this is logarithm base e of 2t plus 2. And the y coordinate in terms of t, y of t, 2 minus 4 times the natural log of 4t. Okay. So, when we're finding the derivative of our curve, dy over dx, or y prime in terms of x, y prime of x, whatever, right? This represents the slope of the tangent line tangent to whatever, curve on the xy plane these represent. Now, I've developed this before in a previous video, so I'm not going to go over it here. If you haven't seen it, that's okay. Just remember this. Use this when you're finding the derivative of a curve represented parametrically. So if you want dy over dx, it's almost like you're dividing the numerator and denominator by dt, even though technically that's not what's happening here. But through some manipulation, you can say that this is equivalent to dy over dt divided by dx over dt. Again, technically you're not dividing by dt here, but you can think of it that way for first derivative stuff. The reason I'm saying this is because later we'll see second derivative stuff that we're going to be asked to do, and this whole dividing by a second differential really doesn't make any sense. So dividing by differential is like technically not correct, but it works out in a lot of the first order stuff, first derivative stuff. We could relabel these as well, right? dy over dt is, you could call that y prime of t, the derivative of y with respect to t. Dx over dt in the denominator here, you could call x prime of t, right? And we can find each of these pretty easily, because of the equations we're given. X and y are both these logarithmic functions of t. And you might recall how to find those derivatives, right? So I'm going to do the derivatives first, right? So we have x of t, take the derivative, x prime of t, or, again, you can call this dx with respect to dt, dx over dt. That's 4 times, I'll simplify it after, 4 times, and then remember the derivative of the natural log of something is the reciprocal of that thing, so 1 over 2t, but then you got the chain rule going on, right? Then you multiply by the derivative of the expression inside, and the derivative of 2t would just be 2. And then plus a constant, so plus 0. So this derivative, after totally simplifying, right, you see the 2's would cancel here, and it's just 4 over t. 4 divided by t. Of course, t must be positive. Maybe I'll point that out somewhere. Because remember, you can only take for real number outputs, right? The expression inside a logarithm must be a positive number, right? So in both of these, t must be positive and not 0 or negative. Okay, so that's going to go in my denominator. And then same thing here for y, derivative of y with respect to t, y prime of t, or dy over dt is, 0, the derivative of the constant. And then you have this negative 4 still times, and then the derivative of the natural log of 4t is 1 over 4t, but then times 4. All right, so you got 4's canceling there, and this is negative 4 divided by t. So when all's said and done here, all right, we're taking on dy over dx, the slope of the tangent line at any point on this curve is going to be, the y prime of t, so that's, negative 4 over t up top, divided by, and then x prime, or dx over dt, which was this 4 over t in the bottom, and you can multiply the top and bottom by t. This is -1. Right. This will end up being -4 divided by 4. The t's would cancel. There you go. So the derivative of this curve, the slope of the tangent line to this curve, is always -1, a constant, which tells me that these two parametric equations trace out a straight line on the xy plane, and that would be a straight line with a slope of -1. And let me I'm going to go to a website now. Let's see this. It's easy to verify visually with lines. So I'm going to go to desmos.com, a free online graphing calculator site, and we'll verify this. I'm going to put in the parametric equations we were given, and we're going to see that, as I change the value of t, the parameter, the curve that is traced out on the xy plane is some line with a slope of -1. So if you want to enter parametric equations in Desmos, you have to enter them like an ordered pair. So left parentheses, and then the x-coordinate in terms of t was 4 times the natural log of 2t plus 2, comma. The y-coordinate in terms of t was 2 minus 4 times the natural log of 4t. And once you do this, it automatically has the range of t be from 0 to 1. Now, I told you t equals 0 is not any good, because you got logarithms here. So I'm not going to go lower than 0, but I will increase the value of t on the right side to say 10 or something. And hopefully you can see it's very clearly is a line with a negative slope. Right? And it might not be that obvious that the slope is -1, but we can plug in some values of t here. And get 2 points on the curve, and problem is there's these logs here, so not gonna have super nice points. I mean, the only ones that'll be nice. Yeah. Let me do this. So I'm gonna do this again. Enter these ordered pairs, but instead of the parameter being called t, I'm gonna call it some other letter, so that way we can see points on the curve be labeled. You'll see what I mean in a second. So instead of, the x-coordinate being 4 times the natural log of 2t, I'm going to call it 2s, and then plus 2, comma, and then 2 minus 4 times the natural log of 4s. So s is replacing t here. I'll add a slider for s and label. All right, so you see when t equals 1, when s equals 1, we're at this point, right? Again, not a nice whole number point or anything. And, you can see as the parameter increases, you're moving down to the right on this line. And if you just took two of these points, say this point here with the 2.7, -1.5, and this point here with 4.35, -3.12, and if you did the rise over the run, change in the y over the change in the x, it should be around -1, right? Approximately, because these are rounded. But yeah, again, looks to me like it is a line with a slope of -1 as we stated. And of course, here in my instructor mode, you can see that the answer was indeed -1. Fantastic. All right. And the exponential equation one should be very similar. Again, all the problems in this same objective should be similar, done in a similar fashion to the way I did this one here. And if you are working, as a student in a Knewton Alta program, once you've entered an answer and submitted it, it'll tell you if you're correct or incorrect, and then give you some sort of explanation afterwards, as to why something is the way it is, why the answer is what it is. I would highly recommend reading through those explanations just to make sure you understand why something is the way it is, why it's right, why you're wrong, and hopefully you can help grasp the material and help you work on future problems. Okay, and thank you very much for watching.